Okay, there we go. Recording should be in progress. And here we go. Good morning, everyone. Welcome to the next installment, session, episode, whatever you will, of EMI test methods. And today's session will be the low frequency portion of conducted susceptibility on primary power leads, also known as CS101, per mil standard 461G. Here's a list of the topics I'm going to be talking about. And so to review from the overview, what this is all in the context of establishing compatibility with the power subsystem. I'm just in a simplistic depiction of a power subsystem. I'm just representing it by a battery here, but you have some common source impedance to get to your distribution point, and then you're hanging loads off of it. So you'll have a load that will be pulling some differential mode current, and the AC ripple current on top of just the DC current draw is what the load needs to operate. But then there'll be some AC current ripple that basically is the noise that is riding on top of that DC current draw. That is what forms your differential mode conducted emissions. Then you will have multiple loads tapped off that common distribution point, and all of the loads will see the combined noise potential at the distribution point. So it'll be formed by the aggregate differential mode current multiplied by the common source impedance. So from a susceptibility standpoint, what we're interested in is the composite noise potential at the distribution point that everyone will see. And that's our conducted susceptibility. So differential mode conducted emissions limits are defined for individual loads. And generally in terms of current, that was the subject of the last session. And conducted susceptibility limits are defined for the worst case composite voltage ripple at the distribution point. So the conducted susceptibility limit really is the thing that your load is going to see. So you could say that's an apples to apples comparison with the behavior of the spacecraft, where a conducted emissions limit is for an individual load, and it's just going to be one part of the composite ripple that will be seen at the distribution point. I think somebody has a hot mic, so can you please mute unless you're asking a question? So again, review from last session that you'll start with the total allowable voltage ripple at the distribution point that all loads will see. And a typical limit, your mileage may vary, but a typical limit is 1 volt peak to peak in the time domain. And from that, we've conducted susceptibility in certainly for CS101 is defined as a frequency swept. You're applying a frequency swept sinusoid. So a typical limit is 1 volt RMS from 30 hertz to 50 megahertz. Now, clearly, if you were to take that 1 volt RMS over that whole frequency range and integrate it into a time domain waveform, you would get considerably more than 1 volt peak to peak in the time domain. And clear, that's clear, that's understood. But just 1 volt RMS is just a good benchmark limit to use as an upper bound. And so we sweep that sinusoid from 30 hertz to 50 megahertz, so you can characterize your equipment susceptibility, to what frequency range might it be more susceptible than others. So it clearly is quite conservative, but if you are sensitive to 1 volt RMS, you want to know about it and then find the threshold. So now I'm going to go into the anatomy of a test method, as I call it. So CS101 is the more recent nomenclature. It used to be CS101. For all practical purposes, they're the same thing. So there's one case where the nomenclature shift doesn't really make a significant difference. It's the same basic test method. But so you'll have some power source and your equipment under test, your EUT. And for most of what we're dealing with on Goddard platforms, we're dealing with a DC power feed. Now all this applies to AC power feeds as well, but mostly we're dealing with DC feeds. And I'm still using the traditional 20 plus 28 volts. Now it's more like 30 to 31 volts, but we're basically talking about the same thing, whether we say 28 volts or 30 volts. A 30 volt-ish DC power feed to your equipment under test. So that's your nominal. That's what you want for the equipment to operate. So now for CS101, we are deliberately injecting some AC ripple through an injection transformer and the transformer is placed in series with your power feed so that you're adding that injected ripple to that 28 volt DC feed. Now, the thing to pay attention to, well, lots to pay attention to, but this first thing is that injected AC potential is going to drop across this full loop. So certainly what you want is for it to drop across the EUT, but some of that injected potential is going to drop across your power source. So you have to pay attention to that. So that's going to be this next part of the discussion here. So looking at the figure in the mill standard, specifically for DC or single phase AC, because recall that the mill standard applies to a wide range of military type platforms, some of which use 3-phase AC. So there's a separate diagram in there for that. So, but we're looking specifically at DC or single phase AC. So here they draw the diagram with power going from right to left, but otherwise it's the same basic figure. But note right here, they put this 10 microfarad capacitor in place to bypass the Lisen impedance. So if you're using Lisens, which, the whole discussion from the last session was why I don't want to use Lisens. But if you're using a Lisen, you've got to put a capacitor here to bypass the Lisen impedance, because that Lisen impedance will drop a significant amount of your injected potential, certainly at lower frequencies. So quoting chapter and verse from the mill standard, which I will do whenever I can to make a point. I'm just going to read this stuff verbatim because I think it's important. But this is in the appendix of the mill standard. The appendix is a really, really useful part of the document because it goes into the engineering basis for a lot of these tests. So this is the section specific to CS101. So below 10 kilohertz, there is a possibility that a portion of the injected signal will drop across the power source rather than the test sample power input. Therefore, below 10 kilohertz, when the specification limit potential cannot be developed across the test sample power input, the pre-calibrated power limit has been reached, it is incumbent on the tester to check that the missing signal level is not being dropped across the power source. If the missing potential is there, usually due to high impedance test facility EMI filters, then steps should be taken to lower the source impedance. This can be done on DC power using a larger capacitor, such as 10,000 microfarad, in parallel with the 10 microfarad capacitor. So we didn't just pull this 10 microfarad capacitor out of the air. It was a specific recommendation here in the mill standard. With AC power, this isn't possible, and the best approach is to bypass facility EMI filters entirely, bringing unfiltered power into the room. Okay, so if you're using 400 hertz power or even 60 hertz power, this 10,000 microfarad is going to filter out some of your intentional power, which you don't want to do. But if you're using DC power, a big honking capacitor is not gonna affect your DC at all. So it works just fine. So we put this. So the capacitor network that I talked at length about in the last few sessions, it's there to decouple your EGSC power supply from the EUT and EMI test equipment. So it's basically performing the same function as decoupling capacitors next to your ICs on a circuit board. So that the AC current that your EUT is trying to draw is going to come from this capacitor network, not from the power supply. It'll provide a path for AC currents, which is going to come into play in an example I'm going to give you in a little bit. And it ensures that the CS101 injected signal drops mostly across the EUT and not across the power supply. This gives you a low impedance down to low frequencies, so that you're always going to have some potential drop here, right? But if you minimize it, most of it's going across the EUT where you want it. And again, this 10,000 microfarad is to be included for DC power feeds only. You'll find out pretty quickly if you try to use that on an AC feed. And also, that's a polarized capacitor, so dropping that potential below zero is also something you'll find out about really quickly, but it's probably better to not put it in the first place. So just a note here, when LISNs are used, you have to modify the configuration for CS101 by putting this 10 microfarad cap or whatever, a 10,000 mic capacitor here. But the point is that if you're basing your configuration on LISNs, you've got to modify the configuration for CS101 and some other tests as well. But when you use the capacitor network, that you set that up once and you leave it alone for all of your tests, including CS101. But by and large, you leave that capacitor network alone for all of your tests. So it's just another fringe benefit of using the capacitor network. So with CS101, you want to monitor the voltage directly across the EUT input terminals. Okay, you want to know exactly what you're putting across the EUT, and because some of that potential is going to drop across your power source. And so you want to place your scope probe across the EUT input terminals. Do not use the monitor terminals on the injection transformer, despite this application note or a figure on the Solar website showing this. I kind of wish they hadn't put this there, and I wish they hadn't put it, but they're again, I'm not making this up. These are recommendations from people who've been doing this for decades. Don't do this. Don't use the monitor. There's a second pair of terminals on the secondary of the solar transformer where you can do this, and you can do it for information. But if you use this as part of your control loop, well, that's only giving you the voltage across the transformer secondary, not what's across the EUT. So you're guessing at how much of this potential is going across the EUT and not across your power source impedance. And we don't like guesswork. You know, let's monitor directly what we're interested in so we know what we're dealing with. Another thing is it is sufficient to inject on the positive side only. In older versions of the mill standard, they specified that you would inject on the positive side and on the negative side, separately, of course. That required reconfiguration, and so basically doubling the test time. And by and large, there wasn't really any benefit to it. So there's no need to inject on the negative side. And that's specifically called out in the mill standard. So one more commercial for using the latest version of a standard. I hear this all the time. Well, we're on contract for mill standard 461E or C or whatever earlier version. There's stuff like this in updated versions of these standards that helps you, that makes your life easier, that makes more efficient use of your test time. So whenever I hear that argument, well, we're under contract for mill standard 461E, whatever. Well, I push back on that very strongly. It's like you owe it to yourself to know what is in these more recent versions of these documents because they update them for a reason. So now the one caveat for not injecting on the negative side, well, unless directed by program needs, such as ISS. Power feeds on ISS are, I've never really understood them, but all of my colleagues who work ISS say that it's, well, there are varying epithets that they use that I won't bother saying here, but it sounds like it's a bit of a mess. And for a lot of those reasons, they say, yeah, you do need to inject on each side individually. But unless you're on a platform like that that tells you you have to do that, injecting on the positive side is sufficient. Now, this is a biggie. The power amplifier of your drive circuit must be powered on and stabilized before you power on the EUT. Probably should have put this in red. I put the rest of it in red. The reason for this is that if the EUT is powered on before the amplifier, well, the entire inductance of your transformer secondary, if you basically have an open circuited primary, this really isn't a transformer anymore. You've basically just got, you know, a 1 millihenry inductor hanging here in series with the power lead. And that has been shown to cause instability and damage. And just a little bit of theory behind this, not a whole lot, so don't worry. But I know that my power subsystem colleagues here, my neighbors in building 20, are quite familiar with this. Highly recommend that you look at this paper. Oh, my apologies. That Spaces link is defunct. I need to update this, but I believe that paper is on the team site. I'll make sure it's there. But there's actually a series of, I think, 3 papers Middlebrook wrote all around that same time frame. But just about stability concerns. I'll give you my synopsis here on the next couple slides. Basically, any interface, any interconnection can be represented with this simplified network model. You've got some voltage source. There's, of course, you can do it as a current source as well. But using the voltage source model, you have a voltage source, some source impedance in series with it, and your load impedance. Okay, and so the output, what I call the VO, the output voltage across the load, just the transfer function of VO over VS, it's simply an impedance divider. And then you can bring the ZL down to the denominator and write it like this. And so if, in general, both the source and load impedances can be complex, inductive or reactive, and I'll give you an example in the next slide, but keeping this general purpose for the moment, they'll have some magnitude and phase. And so you can express the voltage divider this way with magnitude and phase. So if the magnitudes are ever equal and their phases are exactly 180 degrees apart, well, you basically get a divide by 0 thing going on here. You get 1 minus 1 in the denominator. You get a divide by 0 mathematically, but that leads to instability and oscillations and so forth. I mean, the physical interpretation here is that what the source sees here is effectively a 0 impedance, or realistically a very low impedance, right? But it sees a net impedance that is very low. All it knows is, what am I seeing right here? And it's seeing the sum of these two impedances will look essentially like 0 at this point. So voltage source into 0 impedance will give you infinite current theoretically. And so so that's how you get instability and oscillations and so on. If we look at a more specific example here, where our source impedance is inductive and our load impedance is capacitive, which is pretty good general purpose way of looking at things, at least a lot of interfaces. You'll have some filter capacitors at the input of a power converter, for example, and your wiring will be inductive. Well, so we just go through the same impedance divider analysis with inductive and capacitive reactances. Well, 1 over J equals minus J, so you can bring the minus J out front here. Well, so when the inductive reactance equals the capacitive reactance, which it will at some, at whatever that resonant frequency is, that's exactly what a resonance is. In this case, is when the reactances are equal but of opposite phase. Well, there you get your divide by 0 and your instability and oscillations and so forth. So when you have that 1 millihenry inductor, going back to back here. When you have this 1 millihenry inductor in series with your power feed going into what is most likely a significant capacitor network at the input to your power converter, that can lead to instability and damage. So if you turn the power amplifier on first, now it will be a transformer. It will function as a transformer, and the source impedance of your power amplifier will map to the transformer secondary. And we'll talk more about that coming up. And that is essentially a purely resistive impedance. And now you've got a much more stable configuration to turn on your EUT with much less risk of oscillations that can cause damage. And we've seen this. I haven't personally, because people before me learned that lesson, but I have talked to people who before we figured this out, they had their EUT damaged for exactly this reason. They had some horrendous oscillations going on that stressed or damaged some components on the front end of the EUT. So getting back to where we were. Okay. All right. Now, the mil standard 461G setup shows the oscilloscope power is connected through an isolation transformer. That's all well and good, but it's not really necessary. If you use a high impedance differential voltage probe, it eliminates the need for an isolation transformer. And isolation transformers are a little deceiving or misleading. The idea is you think you're floating a piece of equipment with respect to facility ground, and you're really not. That green wire of your power cord, that gets fed right through an isolation transformer. It's giving you a transformer on the power feed, right? So it is isolating the power feed, but the green wire gets fed right through. So it's not really isolating to the extent that you think it is. And the idea is that, for a standard single-ended scope probe, where the negative or the reference lead is connected to the scope case, that you want to float the case with respect to your circuit ground, so that the connection of the scope probe doesn't influence the behavior of the circuit, and it certainly can. So, I mean, it's the right idea, but this may still not work the way you intend it to. The real way to do that is use a high impedance differential voltage probe, so that the both leads, return as well as the positive lead, provide a high impedance path to, well, anything it's connected to, but especially facility ground. That's the real way to do this. And if you do that, you don't need an isolation transformer, and it's simpler and it's a safer setup. Now, differential voltage probes are not particularly cheap, but any EMI lab should have them, and we have a few, and I'm going to show them to you on Wednesday when we hook this stuff up. Another important point, you want to look at AC voltage ripple riding on top of a significant DC level, right? 28 volts, 30 volts. So the default tendency is, well, let me set the scope up for AC coupling, and then I'm only going to be looking at the AC component. Then I can expand the vertical scale to get good resolution of what I'm looking at. Because if you try to expand that vertical scale with that DC level on there, well, it expands everything, right? And then it goes off the screen and you can't see anything. Well, you can still do that when you set the scope up for DC coupling with an offset. And that's a much better way of doing things, in my opinion, because AC coupling can fool you. I probably should, I thought, I just thinking now, I should have put like a depiction of when you put a square wave through AC coupling, just through an AC coupling capacitor. I think everybody has seen what that looks like, right? If it's a fairly slow square wave, slow compared to the charge and discharge characteristics of your capacitor and whatever resistance that it can charge and discharge through, you get a distorted version of the square wave, right? that distorted version, where you get the charge and discharge on the plateaus of the square wave, are not real. It's a manifestation of how you're making the measurement. So when you just set the scope up for DC coupling with an offset, you can set it up for a 28-volt offset and tweak it for whatever it is, 28.1, 28.2. And we'll do that on Wednesday. Then you get that benefit of basically putting the DC level at the center of the scope display, and then you can expand around that point so you can get good resolution on your AC injected signal. And that's what you want. So you can get the best of both worlds, where you're getting the resolution of the signal that you want, but still getting an accurate depiction of it without the AC coupling distorting the waveform. Now, another thing is that AC coupling will mask low frequency drift. And I've got an example here to illustrate. This is a real world thing here that where we actually damaged some hardware. And it was actually the only times in my career that I've been summoned to the center director's office. That's also something I don't really recommend. So here we go. So this is a nameless program. Pay no attention to that clue that I've given you there in that picture. This was, I think, about 10 years ago. But the equipment rack that provided the power to the instrument diode OR'd the prime and redundant power feeds. I think there were multiple power feeds, so I think they did this multiple times. But whatever the case may be, they diode OR'd them. I'm just showing one of those interfaces here because it's sufficient to illustrate the point. But there's a diode in series with the power feed. Okay. Now, from just a purely DC power standpoint, as long as you can handle the power dissipation, the current that's, the power that's dissipated in that diode, and it's just EGSC, okay, no problem, but it actually caused some issues here with CS101, as we're going to talk about here. So there's no capacitor network here. And so when you're injecting your waveform, and the key here was to look at this in terms of current. It was a little bit mysterious when we were just looking at voltage. When we looked in terms of current, that's where everything made sense. So you have some, you have your 28 volts going to the UT. The nominal current draw, as I recall, was on the order of 3 amps. So whatever that nominal DC current draw, let's just use 3 amps as our example here. So now you're applying your CS101 injected signal here. As long as the AC current magnitude, the 0 to peak AC current magnitude, is less than the DC current draw, the net current through the entire cycle of your injected waveform here is always still positive. So the current will flow through the diode, no problem. Everything flows unimpeded through the diode. So even though you're on the negative part of your AC waveform, you have this DC offset that's keeping everything positive. So your net current is always going through the diode in the positive direction. Now, at some frequencies, because remember, your input impedance of the EUT is going to be frequency dependent. Excuse me. And just, with a power converter and a filter bank in front of it, yeah, that input impedance is going to vary with frequency. So without a capacitor network there, well, I'm sorry, let me go down here first. So when you hit a low impedance, a low input impedance, then your current's going to go up, your AC current's going to go up, and it eventually the magnitude of your AC current is going to exceed that DC current draw. Okay, so when you're trying to get to the extreme of that negative part of the waveform, when it's trying to get below 0, well, that means that the net current, what just happened there? Here we go. The net current is now negative, which means it's trying to go that way. Well, Diode isn't going to let you do that. The diode's going to block that current. So the lowest part of the negative cycle is going to be blocked by the diode. So where if everything could flow according to the waveform, where it's trying to go down here, well, the diode's blocking you and it's going to hold you at 0. Okay. So now we look at the voltage, that the voltage is basically going to be held at the 28 volt line. Now, when we're looking at this in terms of voltage, we're going, well, what's going on here? We're at 28 volts. We're not really reverse biasing the diode, so shouldn't be a problem, right? Well, why you got to look at the current, because it's the current that's going to, the diode will block any of the current that's trying to go in that direction. So when you hit the negative part of the waveform, or when the waveform's trying to go negative in terms of current, it blocks the current, then it's also going to stop the voltage from going any further in that negative direction. So without the capacitor network, that injected signal is rectified by the diode, and the resulting half of a sine wave, or really maybe a little more than half a sine wave, but it's a fractional sine wave. And so now your control loop is going to increase the injected level to try to get to the desired test level, depending on how you're monitoring it. If I think in previous days we used a power meter as part of the control loop, or even, I mean, even if you're using a scope, which we do now, it basically is just you set it up to give an RMS voltage, and then it's just that number that's fed to the control loop. The control loop doesn't know anything about the shape of the waveform. It says, oh, my RMS level is below the 1 volt RMS, or whatever the desired level I'm trying to reach. So I need to increase my drive level to get the desired RMS level that I've specified. So it's increasing the level even more because it can't quite give you that because it's an asymmetric waveform. See how this starts to run away from you? So then another part of the puzzle is, excuse me, think about going back to thinking about the current. During the positive part of the cycle, the current is going into the EUT and charging up. I'm just simplistically representing input filter as just a capacitor bank here. So the current is charging up that capacitance. But then during the negative part of the cycle, because it's asymmetric, it's not getting all the way down to the full level to discharge that capacitance. The capacitance doesn't fully discharge, right? It's hitting the diode. The current's not getting all the way down to the level to fully discharge the capacitance from what you put into it in the first half of the cycle. So what that means is that on each cycle, there's some net charge that's still on the capacitor. You're not completely discharging it. But with a fully symmetric waveform, you charge, you discharge, and everything is still just riding on that DC level, right? It's still centered on that level. Okay, everybody with me? So what ends up happening is that you get this slow upward drift of this waveform. And if you're AC coupled, you won't see that. And that's what happened. We didn't actually observe this until we saw that the DC level, there was telemetry, I think, in the EGSC that showed, hey, that DC level reached, got up to over 40 volts or whatever it was. So there's this slow upward drift, eventual overvoltage, and stress and damage to front end components of your EUT. And this was flight hardware. Sort of doesn't matter. Even if it's an EM, that's a bad thing if you stressed or damaged components. But it was flight hardware, and it was, an undesirable situation, definitely a PR, and then FRB and all the rest of it. And then I got summoned to the principal's office to explain what happened and how we were going to make sure this didn't happen again. So that capacitor network provides a path for AC currents. right? So that's one of the benefits there, is that with that capacitor network there, on the negative part of the cycle, that current can flow freely. You have a symmetric waveform and all as well. Okay, I believe that, yeah, that's the last chart. Anybody have any questions on that? Okay, now we'll keep moving. All right, so shifting gears a little bit here. The default, or the first thing you think about with CS101 is the voltage limit. Okay, and so going to the mill standard here, the limit curves in the mill standard are what are shown here, and it's 2 volts RMS at this low frequency plateau up to 5 kilohertz. For curve number 2, that's 28 volts or below. So we tended to use that as our default. And then above 28 volts is this 6.3 volt RMS level. Now remember, the mill standard is used for large military platforms that a lot of which use AC power systems, 120 volt, 60 hertz, and so on. So 6.3 volts of ripple on a 128 volt system, it's about 5%. It's I'm sure a little bit conservative, but it's not really outlandish. But 6.3 volts RMS on a 28 volt DC system is beyond ridiculous. There's really no compelling reason to ever use this. And even 2 volts RMS is a bit extreme. So I'll get to what we use in GEVs here in just a moment. But the voltage limit is only part of the limit. If you're only specifying a voltage limit, it's an incomplete requirement. There is always effectively a current limit. The default is that it is specified as a power limit, and I'll talk about what this means because it can be a little confusing. That the requirement is also met when the power source is adjusted to dissipate the power level shown in the figure into a half ohm load, and the EUT is not susceptible. So we'll talk at length about what this means, because it's the wording is less than ideal, but bear with me and we'll go through this. But the default limit in the mill standard, they just have this one line, and it's 80 watts in this low frequency plateau up to 5 kilohertz. Now this corresponds to curve number 1, the 6.3 volts RMS into the specified half ohm calibration load. Right, just V squared over R. You square 6.3 volts, divide by half an ohm, you get, 80 watts, 79 point whatever. And that's all they specify is this one curve. And this is actually a comment I submitted. Mill standard 461H is in review. It's in the process of being updated now. I submitted a comment about this, and I don't know if they're actually going to implement it. I should check in with it. I mean, I know the people who are working on the committee, but I submitted a comment that they should update this to indicate that the power limit should be consistent with your voltage limit. And I'm going to talk about the importance of that here in the next several slides. So the default limit we use in GEVs is 1 volt RMS. That generally is sufficient to bracket anything we would have on a 28 volt DC bus. And then that 1 volt into across a half ohm load is going to correspond to 2 watts. So 2 watts versus 80, that's a pretty significant difference. And we'll talk about the implications of that in terms of current here coming right up. But what is this pre-calibration step doing exactly? Well, as shown here, you have your signal generator through your power amplifier. And before you ever hook it up to your unit under test, before you hook it up in series with your power feed to the unit under test, you just hook it up to this half ohm load. So what you're doing is you're recording the signal generator level at each frequency required to dissipate the specified power into a half ohm load. Now, this test method goes back decades. Why they specified it in terms of power, I'm not really sure. But I think they could have simply said required to put the desired, your voltage limit, right? In our case, 1 volt RMS, but whatever it is, if they just say, record the signal generator level required to establish your desired voltage limit across the half ohm load, it would basically be the same thing. When you specify it as a power limit, it kind of implies that, this is the confusion that I've had and other people have had, it sort of implies you're monitoring power in real time while you're injecting into the EUT, and that's not what you're doing. It's all about pre-calibrating the levels into a specific load. So anyway, when you say required to dissipate the specified power, it's the same as saying your specified voltage limit. So these become not to exceed values when you're applying your signal to the EUT. So, you know, you're pre-calibrating into a known standardized impedance here, half an ohm. And so if your impedance, the load impedance of your EUT is not going to be half an ohm, it'll just be happenstance at whatever frequency it might be that, but by and large, it's not going to be half an ohm. So whenever it's greater than half an ohm, you can get your 1 volt RMS all day long. Both voltage sources love high impedance, but when that impedance goes below half an ohm, like it will at the input filter to a power converter or the converter itself, that the input impedance will drop to something that looks pretty close to a short circuit. So if you keep trying to inject your 1 volt RMS into a short circuit, your current will go through the roof and you can burn up hardware. So you need to specify a current limit one way or another. And we'll talk about the different methods of doing that. This is one. But so the default method is to do this pre-calibration and establish these not to exceed levels. Right. So that if you hit that not to exceed level before you get to the 1 volt RMS, you stop. And going back to how the requirement is worded, this highlighted wording here, the requirement is also met when the power source is adjusted to dissipate the power level shown in the figure, blah, blah, blah. So what that means is that if you hit that pre-calibrated level first without being able to establish the voltage limit, you're still meeting the requirement. I've gotten many waiver requests from people, when this happens, oh, we weren't able to get the voltage limit because we power limited. And, I'm able to pass along the good news is, no, you don't need a waiver for that. You met the requirement, right? You did exactly what you were supposed to do. You met the requirement. You don't need a waiver for that. So anyway, EMI engineers are quite used to making people unhappy. So when I give them news that makes them happy, I relish that. Anyway, not that I enjoy making people unhappy, but that's probably enough said there. Anyway, so here's the pre-calibration equivalent circuit with the transformer. So you have your power amplifier with its physical output impedance, and it's a 2-to-1 step-down transformer, and into your half ohm load. So we can simplify this equivalent circuit just mapping things to the transformer secondary. Okay, so since it's a 2-to-1 step-down transformer, then your effective source impedance referred to the secondary is going to be 1/4 of the physical output impedance of your power amplifier. Okay, hope this is clear. This is going to be central to everything that's coming up here. So is everybody with me? Okay. So the pre-calibration step sets the maximum. Yeah, the pre-calibration step sets the maximum source potential at each frequency. So you sweep across the frequency range, and you basically are creating a lookup table of what your maximum drive level is at each frequency to get the desired potential. In our case, 1 volt RMS across the half ohm calibration resistance. So the first thing that's doing is that it's setting your open circuit potential. Okay, so it'll establish at each frequency the open circuit potential VOC for when the input impedance of your EUT goes to infinity. Okay, now your control loop is going to limit you to the desired potential, right? So theoretically, you should never reach this, but we'll get to a case where you have to pay attention to this. But the more immediate significance of this open circuit potential is that now if you look at the case where you have a short circuit, which you will have some low impedances at some frequencies for power converter input, the short circuit current is determined by the open circuit potential divided by the source impedance. So for any kind of drive circuit, you do want some non-zero source impedance here to limit the current. Okay. Now, the thing to note is that this short circuit current is going to depend directly on this source impedance, which is not specified or controlled. Okay. The traditional amplifiers used for CS101 and CS101 have defaulted to, or generally have a physical output impedance of 2 ohms, which maps to half an ohm at the transformer secondary to match the half ohm calibration load. But that's not specified in the mill standard. It's kind of and I'll talk about a couple cases here where that can get you in trouble. So, but if you are using one of these standard amplifiers, which we do here at Goddard, you know, and I'll show you that one on Wednesday when we're in the lab. But when your physical output impedance is 2 ohms, mapping to half an ohm at the transformer secondary. If you look at that default 80 watt limit, that gives you an open circuit potential of twice 6.3 volts at 12.6 volts RMS, and a short circuit current of 25 amps. If you use the GEV's 2 watt limit, that gives you an open circuit potential of 2 volts RMS and a short circuit current of 4 amps. So if you just default to the mill standard 80 watt limit, you're going to get a little more than 6 times the 6 times higher short circuit current than what you really want if you're using a 1 volt RMS limit. That's why you must pay attention to these things. You must pay attention to your power limit or current limit, as well as the voltage limit. It's an incomplete limit, and it's very unsafe to just specify a voltage limit with nothing else. So this is one of the things I look for whenever I'm asked to review requirements. I see this all the time where there's just a voltage limit for CS101. And you got to specify a pre-calibrated power limit or a current limit, or in a lot of cases we just specify both, and give the option of which method you want to use. So let's look at an example where we have a low source impedance. So if it low with respect to the pre-calibration impedance, right? So if R naught, the physical impedance in the power amplifier, is less than 2 ohms, so that the effective source impedance is less than half an ohm. So, you know, everything with respect to that calibration impedance. Well, there's a specific example that I encountered at a nameless test facility. Wasn't here at Goddard. Their source impedance, they were using an amplifier with it was a specified source impedance of less than half an ohm. So I'm just going to use half an ohm as an example here. And so that maps to an effective source impedance of 1/8 of an ohm. So when you just do the voltage divider to get 1 volt RMS or 2 watts across our calibration load, our open circuit potential is 1.25 volts. That doesn't sound too bad, right? That sounds fairly benign. But when you drop that 1.25 volts across 1/8 of an ohm, well, you can get 10 amps of short circuit current. And that's, you know, more than double the 4 amps that you really want for a 1 volt load. Now, and what this particular lab did was, after they did the pre-calibration, they actually did a verification where they threw a short circuit out there and played back the levels, and they were getting, I think, 12 to 15 amps RMS. So remember, the spec was, you know, no greater than half an ohm. So there clearly the impedance was a little bit less than that. Mm-hmm. So we were getting, you know, 12 to 15 amps. you know, and then I looked up the spec for the amplifier they were using and saw, okay, 0.5 ohm. But if you're using an amplifier with a lower source impedance than the I can't say standard because it's not actually specified. It was just sort of, I guess, understood for a number of years that you would use an amplifier with a 2 ohm source impedance, but it's not really specified. So if your lab is using a more garden variety audio frequency amplifier, it may have a much lower source impedance, which can give you a much higher current than you might be bargaining for. On the other side of it, what if you're using an amplifier with a higher impedance, so higher than 2 ohms, or a higher effective impedance than 0.5 ohm? Well, I was drawn into this investigation where it turned out this lab was using a drive amplifier with a source impedance of 50 ohms. Not too surprising. That's a pretty standardized value, right? A lot of amplifiers. There are a lot of RF amplifiers that go down to very low frequencies, and so this lab had one that went down to the 30 hertz. That's what they used for CS101 or 101. So that 50 ohms maps to 12.5 ohms at the transformer secondary. So when you're calibrating to 1 volt, well, your open circuit potential is about 26 volts. Does that sound like a good idea? And so your short circuit current is fairly benign because of the high source the high source impedance. That 26 volts dropping across 12.5 ohms is just over 2 amps RMS. Now, okay, you might argue, well, we have a control loop in there that's limiting us to 1 volt RMS, right? And sure, that's what's supposed to happen. But in their case, that control loop stopped working for whatever reason. I don't remember exactly what happened there, but the control loop stopped limiting to 1 volt RMS. So they were applying the entire open circuit potential into their equipment under test. So applying 26 volts on top of a 28 volt feed, and I think in their case it might have been 120 volt feed, but whatever the case may be, when you think you're limiting to 1 volt and you accidentally apply 26 volts, that's not a good day. So they were definitely not using an appropriate amplifier here. And I said, do not continue those tests until you get an amplifier. I don't think they had one. I think they had to go rent one, but I said, do not use that amplifier again for this test. That is not safe. It's dangerous. So now an alternative, and this is the alternative I recommend, and this is what we do at Goddard. Directly monitor and control the current into the UT with a clamp-on current probe. Just put a current probe around the power feed, and if your control loop can accommodate it, include it in the control loop. So you're first trying to establish your desired potential. So in our the default is 1 volt RMS, and then limit the current to 4 amps RMS. So if you hit 4 amps before you reach 1 volt, stop. And again, you meet the requirement. There's no waiver. You're meeting the requirement whether you hit 1 volt RMS or whether you hit 4 amps first. And a fringe benefit here is that this provides a measurement of the UT input impedance when you're measuring the voltage injected, which you are, right? You're monitoring the injected potential, and so you record these values here. You'll be able to characterize the input impedance of your EUT, and sometimes people do that. Okay, I'm going to wrap up here with an example of some transient events that can occur. Does anybody have any questions on what I've got so far? That's kind of the extent of the basic test method itself. But now I'm going to talk about some undesirable things that can happen with your test equipment. So we have a question? Okay, so a recent example, this was a year ago, something like that, maybe 1 or 2 years ago. During CS101 testing on RST C&DH unit, transients from the setup caused the overcurrent protection circuit on the SCOM card to switch off. And there's a whole detailed investigation there that I'm not going to go into, but basically that there was this overcurrent protection circuit that was tripping, and we determined that it was a result of these transient events coming from our test setup. And so one of the main things was, well, we wanted to characterize the setup, like why was this happening, but also were the levels that they produce levels that could have posed a potential damage risk to the play hardware. That was more. I guess I just copied this chart from that investigation. The real thing pertinent to this discussion is just understanding what your test equipment is doing. And fortunately, we didn't actually damage hardware, but we had these anomalous things happen during testing that just caused a little bit of a delay to the test campaign. We had to change the circuit in the CNDH unit to be less susceptible. But anyway, here's what happened. So we characterized our signal generator. I just ran the signal generator right into the scope, I believe here. To first characterize what happens when you change frequencies. And so from all, we did this numerous times. Every time you change frequencies, the frequency transition happened at a zero crossing, which is great. That's kind of what you want. There was no abrupt or sudden change in level when you went from one frequency to another. So they clearly put smarts inside the signal generator to make those transitions happen at a zero crossing. But when we looked at a level shift, because what you're doing with this, when we were in the lab on Wednesday, I'll demonstrate this a bit. But when you go from one frequency to the next, you want to drop the level, then shift up to the next frequency, then bring the level back up to minimize any risk of if you hit a resonance or the impedance starts to drop, the level can the level can shift pretty significantly going from one frequency to another. So you drop the level by 6 or maybe 12 dB, move up to the next level, and then bring it back up. So level shifts are also a significant part of the process. So first thing, and this was right in the data sheet for the signal generator, the levels during any transition stay within the desired limits. So that's great. And that's so the absolute magnitude of the levels during any of these transitions stayed within the desired limits. So far so good. But transitions tended to occur at random phases of the start and end waveform. While they had the smarts in the unit to make the frequency transitions occur at zero crossings, they didn't do that for level transitions. I have no idea why. But so when you're transitioning from one level to another, you get these very abrupt transitions, right? The worst case is you're going from like the extreme end of the waveform and it slams to zero. You can kind of see it right there. And it's not at the extreme end, but you're not at zero, and then it just slams to zero, and then wherever you are here, it goes from zero to, in that case, it is pretty close to the full amplitude. So again, with a lot of these circuits, it's the DIDT or the dVdt rather than the absolute magnitude of either that can cause problems. And here this is most likely relay chatter. We could actually hear the relays clicking inside the unit when it was most likely going from one drive circuit to another, to get you from one drive level range to another range. So you could hear the relay chatter as it was making those transitions, and it was giving you these abrupt or this kind of ringing here before at the level actually settled down. So when we characterized this into a capacitive load here, we threw 10 microfarads out here, and this was an expanded view here. If we zoom in on these waveforms, we could see a definitely an abrupt transition here when the level just slammed full on from zero, and going into a capacitive load, you get a pretty significant amount of current there. So I'm just illustrating that the test equipment can be behaving in ways that you may not necessarily expect. Now, we've tested a lot of units with this same setup and not experienced this kind of problem. So these kind of transients are a little bit more of an extreme test than if it were a completely clean sinusoid. And that was an interesting discussion when we realized what was happening. The box provider initially was saying, well, you're testing us to more extreme conditions than the test method requires. We shouldn't really, we shouldn't have to, be in compliance with these non-standard things that the test is doing. And, I can't fault them for making that argument. I didn't buy it, but I couldn't fault them for making that argument. But I did point out, and also to project management, who came down to the lab while we were, troubleshooting this. The manager who came down to the lab, who I've known pretty much my whole career, I took her aside and said, do you really want to fly? This is the flight computer, by the way. This is the spacecraft command and data handling box. So this was the flight computer for the spacecraft. So the stakes were a little bit higher here. I said, do you want that flight computer just switching off at unexpected times during the mission for any kind of transients like this that we might not be able to predict? And of course, the answer was no. Eventually, everyone got on board, said, yeah, we need to fix this. And we actually, most of us, I think, looked at it as a fortunate thing that we did actually discover the susceptibility that we wouldn't have seen if it was just a straight up CS101 test. That had we not discovered this during test, the flight computer could possibly just switch off if we saw these kind of transients on the power line during the mission. So we did fix it, and now we have a much more robust system. It caused about a month of schedule delay, and it hurt. But I think everybody, once we realized what we were dealing with, felt better about, yeah, that was a month well spent to make sure that we don't have this sort of thing happen on orbit. And to summarize, so the capacitor network minimizes the potential drop across the power source impedance, and it maximizes the drop across the UT, which is what you want. You want ideally all of the energy that you're injecting to go across the EUT. You want to directly monitor the injected potential across the EUT input terminals, use a high impedance differential voltage probe, and use DC coupling with an offset. Avoid AC coupling. It can fool you and hide things from you. The signal injection on the positive power lead is sufficient unless directed by program needs, such as ISS. Here's the biggie. They're all tied for first place, but this one's extra first place. Injection equipment, especially the drive amplifier, must be powered on and stabilized before powering on the EUT. It minimizes instability risks, and it maximizes hardware safety, which I think that's what everybody wants. The injected potential is only part of the limit. There must be a current limit specified one way or another, whether it's directly current monitoring and control, which is what I recommend, or if you're using the pre-calibration method, pay extra close attention to that source impedance of your drive amplifier. Because if it's anything significantly far from what should have been a standard 2 ohm impedance, you could be getting a very different short circuit current than what you expect. And you want to characterize your signal generator for transients during those frequency and level transitions. So that may cause unexpected behavior during test. And advanced knowledge preparation. That's a very awkwardly worded phrase there. My apologies. But advanced preparation can only help when anomalies occur. Okay? So if you start seeing these anomalies during test, if you have some advanced knowledge of it, you can get a jump on things when you see these strange things happen. Oh, okay, I think we know what's happening here because our test equipment can have some of these transients, so forth. That is what I have. Anybody have any questions? None at all? Anybody still there?
Yes.
Yes, we're still on.
Well, okay. I'm only 7 minutes tardy for my 10 o'clock. So thank you all for listening. And for those of you who can join, we'll be in the lab on Wednesday to illustrate some of these things. For next week's sessions, I'm gonna cover CS114. I may end up having to do those Tuesday and Wednesday because I may not be available on Monday. But stay tuned. I will send an email once I know what my plans are. So with that, thank you very much. I'll make the recording available later today, and have a good day.
Hi, John.
Thank you.